Hi, welcome to my talk. I'm Bodong Zhao from Tsinghua University. I'm going to introduce our work, StateFuzz. As we know, code coverage-guided fuzzing using genetic algorithm is now a very useful solution for finding bugs. A code coverage-guided fuzzer first selects seed from seed corpus and mutates it to generate a new test case. Then the fuzzer executes the instrumented programs with test case and receive feedback. Based on feedback, the fuzzer checks whether the whether the test case hit new code. If so, the fuzzer preserves this test case in seed corpus as a new seed. However, code coverage-guided fuzzing has limitations in fuzzing rich state targets. Here is an example. The function action receives OP and value from users for taking different actions, including set A, set B, and the VUL function. There is an auto-bound bug in the VUL function. To trigger this bug, we need to set the state A to 0xFF and the state B to buff size. Then we execute the VUL function. If we further this example program with code coverage-guided fuzzers, we will find such a dilemma. In the beginning, many test cases hit new code and are preserved. The test case 1, test case 2, test case 3. For now, as we can see, all codes are covered and no new code to hit. As a result, no more test case will be saved. Even though this test case can set the correct states, and the states can easily be changed by subsequent test case. So it seems difficult to trigger the bug. There is no seeds in corpus that can set the correct states. The main reason is that code coverage-guided fuzzers will ignore test cases that exercise the same code path, even though they have explored the new states. We need a state-aware fuzzer. So how to perform state-aware fuzzing? We summarize 3 questions to answer. First, what are program states? Second, how to recognize the program states and track them during fuzzing. Third, how to use program states to guide fuzzing. For the first question, essentially a program state is the execution context of a program, including values of all memory and registers. However, the number of such states is too large, and it is hard to track them all in practice. Thus, we believe that a practical fuzzer has to focus on a subset of program states. Recent work has proposed several solutions for representing program states. Researchers propose to manually annotate the target programs and use annotated data as program states. Such manual annotation will involve many human efforts. Protocol status code can also be used to represent program states. However, status code is not always available. We find it very common in programs to use variables to represent program states. So, we propose that we can only focus on a subset of program states represented by variables. As a result, the second question is equivalent to how to recognize the variables that represent program states. And we name these variables that represent program states as state variables. We summarize the features of state variables as follows. First, these variables have a long lifetime that can span different program states to record state of information. Second, they can be updated by users for status transition. Third, since the program state always controls the program's behavior, these variables should be able to affect the program's control flow or memory access. We observed that rich state programs always require multi-stage input, and the different stage of inputs will trigger different program actions. For example, a FTP server will receive multiple packets from the client. The FTP user and the FTP pass action will be triggered by a user a user packet and a path packet. The Linux kernel may receive many system calls from user space programs, and the handlers in file operations will be triggered by these calls. We also observed that state variables are usually shared by different program actions. For example, the variable access is read by the FTP list action and updated by FTP path action. Therefore, we can recognize state variables by extracting the variables that have a long lifetime and shared by program actions. Then we track program states by monitoring the state variables. For the third question, a straightforward idea is using state coverage as feedback for fuzzing. However, if we use a new value of state variables as a new state, there are too many values, and a lot of test cases will be preserved, causing seed queue explosion and hurt the performance of fuzzing. So we can merge values representing the same state and divide each state variable's value space into several ranges. Therefore, we proposed that instead of tracking values, we track special value ranges and extreme values of state variables as feedback of fuzzing. We built a prototype of StateFuzz for Linux driver fuzzing. This is workflow of StateFuzz. It includes three major phases. The program state recognition stage first analyzes the source code of Linux drivers to recognize program states, including the state variable list, the state variable value ranges. Then the instrumentation stage instrument the target program to track the program state coverage, along with code coverage. In the fuzzing loop stage, we extended the fuzzing loop of code coverage get the fuzzers by applying the program state feedback to seed preservation and the seed selection. In the program state recognition stage, we first need to identify program actions. In Linux drivers, the program actions are the handlers that can be invoked via system calls. We use inter-procedure and path-sensitive analysis based on diffuse to identify program actions. We use an HPET driver example to show how we recognize state variables with static analysis. We first identify program actions and their code lines. Then we extract the variables accessed by these code lines. As we can see, the variable HDWIRQ in red is read by action 2 and updated by action 1, and it has a long lifetime, so we add this variable into our state variable list. We use intro procedure and path-sensitive static symbolic execution to infer state variables value ranges. For example, from the conditional statement in line 11, we can infer 3 value ranges. In the fuzzing loop, StateFuzz uses a 3-dimension feedback mechanism to guide state exploration. It issues 3 types of feedback signals when a test case hits new code, new value range, or new extreme values. Then the fuzzers preserve the test case in different tiers of corpus based on the feedback types, and the fuzzer will select the seeds from these 3 tiers of corpus. StateFuzz is implemented based on several open source projects. We thank the authors for their awesome projects. To evaluate the effectiveness of StateFuzz, we designed several experiments and tried to answer the following questions. We conduct experiments for Linux drivers in 2 environments, including the Linux upstream kernel on QEMU and the Qualcomm MSM kernel on a Google Pixel phone. We recognized about 6,000 and 5,000 state variables from the Linux kernel and the MSM kernel respectively. On average, we recognized about 3 value ranges for every state variable. Then we investigate the semantic of state variables by analyzing variable names in the abstract syntax tree. The result is shown in the pie chart. We also analyzed the false positives and the false negatives. The results show StateFuzz can recognize 90% state variables and the precision is 40%. We believe that fuzzing can tolerate some false positives because of its fast execution speed. Our experiments shows that StateFuzz can achieve higher state coverage and code coverage. Specifically, in the Linux kernel, StateFuzz achieves 32% higher value range coverage than Syzkaller in Linux kernel, and 19% higher code coverage than Syzkaller. More details are shown in our paper. In summary, a total of 20 vulnerabilities are found by StateFuzz. We reported all these 20 vulnerabilities to developers, and 19 of them are confirmed. Among the 19 confirmed vulnerabilities, 14 are assigned CVIDs. In the future, we will continue to apply StateFuzz to network service fuzzing and apply StateFuzz to other Linux drivers that interact with users through multiple I/O channels rather than system calls. In summary, we present a new fuzzing solution, StateFuzz, for fuzzing rich states programs. StateFuzz models programs states with state variables. We implemented a prototype for fuzzing Linux drivers. Experience shows that StateFuzz has better performance than Syzkaller in fuzzing Linux drivers. Thanks for listening. Any questions are welcome.